So supposing you have a let me see what notation did I use here. I guess I can stick with capital, or let me say n. Supposing there are n numbered, let me say this is 1. Two balls, right? So they have numbers. When I say n numbered balls, it's automatic that the numbering is from 1 to n, right? Don't ask what numbers are there. 1 by 1, right, which is the same as without replacement, right? You draw 1 by 1. Now, this is the experiment, simple. You are drawing them at random, just putting your hand in there and pulling out 2 balls. So what are the 2 automatically definable random variables? X is, for example, right, the number on the first ball, and y is the number on the second ball. Y by definition is the number on the second ball. This is enough to ask, or apply all this notation to this problem, right? This information is sufficient to be able to do it. So first of all, what are the, right, the experiment is not complete until you have drawn the second ball. So obviously at every drawing you have a value of capital X, you have a value of capital Y, right? So what is this omega xy now? If I want to write it mathematically, how will I write it? It's the sum of all numbers, integers, natural numbers ij for 0 less than I, 1 less than I, comma j less than n, but I cannot, you can say it like this, right? I obviously cannot be equal to j in this. Why? Because once you have drawn number I cannot, I do not have that number again to draw again, right? So j cannot be equal to I. Okay. So what is the probability of this? And it turns out that it does not matter what the numbers are, the pxy, okay. Before that, let me also look at omega x and omega I. When you can also look at the random variables individually. So what are omega x and omega I? Note omega from our usual, the old theory which applies completely in toto. So omega x will clearly be the number. So for both omega x and y, you can get all the numbers from 1 to n. Note that this is not sufficient to tell you the nuances of this, right? This will not tell you that you cannot get I not equal to j. In fact, if you did it with replacement, you threw the ball back, then you would still get the same omega x and omega y, but omega xy will be every possible pair. You can even get II when you do with replacement. But I have said here clearly you are drawing it without replacement 1 by 1. So that clearly tells you that I cannot be equal to j. So what is the probability for this case? Which implies that pxy of I comma j. Now I do not have to necessarily use xy. Remember, right, the convention is the values the random variables take are written in the order of the subscripts. So if you write pxy, the first one is going to be for x and the second one for y. Okay, and this is y. That makes no sense to write pxx, right? So it is pxy. If you want to write pyx, that's fine, but make sure that you do the the arguments appropriately. So it turns out that pxy ij is 1 by n into n minus 1 for all ij, all pairs ij in omega xy in here. How do I know this? It's obvious, right, or not so obvious? Just we have done this earlier, right? So you draw the first ball, what is and conditioned on that, supposing what is the probability that x equal to I? 1 by n. So given that x equal to I, what is the probability y equal to j? For j not equal to I, it will be 1 by n minus 1. So probability of, so this is basically, you think of this as probability of this is equal to probability of capital P of y equal to j given x equal to I into probability of x equal to I, right, which is 1 by n minus 1 into 1 by n for j not equal to I, and it is 0 for j equals I if you want to insist on setting j equal to I if you want. In fact, it is somewhat inconvenient to leave out these diagonal entries in that if you write as a table. So sometimes they expand omega xy to include those another countable collection and then attach 0 probabilities to those points. That is perfectly alright, right. So you could say in some other specification you could say you could move this part to here. Instead of saying for all ij you could say pxy ij is 1 by n minus n to n as long as I is not equal to j and equal to 0 for I equal to j. You could say that also. So you should be flexible. Do not insist that this has to be part of this. I am just writing it like that for convenience out here. So everyone is agreed that it is 1 by n into n minus 1, this is correct. So do these guys add up to 1? They must, they will. Go look at how many entries do you have in that square. You do not have the diagonal entries, right, you have n into n minus 1 off diagonal entries, so each of them has 1 by n, so it definitely adds up to 1, right. So if I e.g. for example if I take n equal to 3 or something, I will get 0 0 0 on the diagonals. So this will be y, this will be x, x can take the values 1 2 3, this x can take, y can take values 1 2 3. What will be all these points out here? Everything will be, what will be the probabilities here. So here I am going to put probabilities 1 by 6, right, and you have exactly 1 2 3 4 5 6 positions. So okay, so this is just to make sure that, right, there is absolutely no ambiguity in understanding this very important concept, right, of the joint PMF itself. Note that given some experiment like this, we can define, these are not the only two, I can define any whatever random variables I want. I can define x to be okay first number, the first number. I can define y to be the bigger of the two. Y should in some way involve the second one, right, that is all, because the experiment consists on drawing two balls. Well, you can say if you define okay, let us assume alright, so and what about I can define x to be the sum of the two and y to be the difference of the two. I can do all anything I want, they will still be random variables, right. So we will generalize this a little bit. So in other words, there is no restriction that you have to define it in the simplest way, although it makes some sense to define it in the simplest way possible and then think of the other random variables as derived from these two by some algebraic operation. For example, if I say x is the square root on the first ball and y is the third power of the second ball, you can obtain that by transformation. All this we will study formally little later, but for right now let me take the simplest possible definition, which is this, and so work it out only for that, which I have done here. Then I want to define what are called marginal PMFs. Given this joint PMF, can I obtain from it marginal PMF? What do I mean by marginal? That is, if I go like this and add, what do I get the probability of? I get the probability that x is equal to 1 if I add horizontally. If I add vertically, I get the probability that y equal to whatever, 1, 2 or 3. So you can calculate the marginal PMF this, knowing this pxy can tell you both px as well as py. So what is this px? This px of x, so before that, okay, so again, I mean, to do this, the first step is to identify clearly omega x and omega y. Right. So, so the step is find omega x and omega xy, omega y from omega xy. This, there is no magic formula for this. You have to look at the structure of the omega xy and determine, right, all the points that, all the values that x can take. So from this it should be clear, right, what this is and what this is. And then this step is, right, in many cases, many times it's not emphasized, but it's very important, because even before you find the probabilities, you have to look at the possibilities, right. What are the possible values of x? Then for x in omega x, Px of x is going to be what? Obtained by summation over appropriate y. Appropriate values of y, Pxy, here x is fixed. In this summation x is fixed, you are only, right, taking the summation over y. And you are repeating this for all x in omega x. You freeze this x, then look at all those points. If I have something like this, if I freeze some value of x, I may have some 3 points here, right. So this could be xy1, xy2, xy3. I have to add all those probabilities and get this. If I go to a different value of x, I can get some whatever number of points. If it turns out there is no grid at all, then there may be only a 1-to-1 mapping between this and this. It may happen that all these points are so funnily located that there is no, right, nothing in common, right, no coordinates in common. Similarly, Px of y, Py of y. If you go like this, y, you find by adding all these probabilities you will get Py of y. Why are they called marginal PMFs or marginal probabilities? Because in this table, where would you write them? You would write them on the margins here and here. So you write the marginal probabilities on the margins of the table. That's why, that's a nice way of remembering why they are called that. Okay. So clearly in this problem it's very simple. P of x equal to I has to be 1 by 3 and P of y equal to I also has to be 1 by 3. So it does not matter which ball you draw, which x and y have the same same marginal PMF, and what is important is that you cannot get the in general you cannot get this joint PMF by looking at the marginal PMFs alone. You can only go from joint to the marginal. You cannot go in the opposite direction in general. There is a very important special case where you can, but in general you cannot. So if I want to say this clearly, e.g. for two balls drawn, omega x, I think, let me write it again, 1, 2 up to n, and Px of I equal to 1 by n, that is equal to omega y. I've already written it here, does not matter, write it again. This is equal to Py of j, if you will, if you want. Sometimes it's nicer to stick to the original notation ij, right, or xy, just to keep your thinking straight. There is no reason why, of course, I cannot use I here. I could use I here, there also, right, after all, a dummy argument, but it's just better to, if you start out with Pxy of I comma j, it's better to stick to j here. And certainly it's convenient here to stick to y. So likewise for, I'll write here okay, only thing is here you might want to put, if you if you have subscripts, I mean, so if you have trouble when you review this material, you could put a subscript x naught if you want, but no, people usually don't do it, so we won't write it. Okay, I think let's not spend more time on this. So you can always, what I want to say, the message is that, so which implies we can always find marginal from joint. But not reverse. That is, you cannot get the joint from the marginal in general. I think this example is clear, right? There is no way that somebody tells you that these are the two, right, marginal PMFs of x and y to get that particular joint PMF, right, 1 by n into n minus 1, you just cannot get it, right? Because this same joint PMF also comes when you do balls with replacement. But when you do balls with replacement, it turns out that the second drawing is completely independent of the first drawing, and you get a totally different totally different joint PMF. We will have to say that for a little bit, but anyway, so you cannot do the reverse calculation, right, and this has to be kept in mind.